I have a great pleasure of introducing you Chun Peng. He's associate professor in the Department of Logistics Management in Beijing, Jiaotong University. But more than that, he's a member of the great family of GERAD. He was a postdoc at HEC Montréal, and student of GERAD. His research focuses on data-driven decision-making under uncertainty, and he applies it mainly to logistics, transportation, and supply chain management. We have co-authored papers together in landmark journals, but he also has many other successful publications, including in operations research, transportation science, Omega. His research is funded by the National Natural Science Foundation of China. So thank you for visiting us. It's a real privilege to have you with us at the time.
Okay.
This talk will be followed by 2 p.m. 3 p.m.
Yeah.
With another talk. So please stay with us.
Okay.
Floor is yours.
Okay. Thanks, Erica, for the introduction. And it's my great pleasure to give a talk in the GERAD again. I remember that before. I think my first talk is I presented my transportation science paper in this room. Yeah, I think a couple of years ago. Yeah, and Montreal is actually I would say Montreal is my third hometown actually. Yeah, before my hometown, I was born in Beijing. I studied my my master, my PhD here. Then is Montreal. So today this is a recent research. It's this is doing work with my colleague Mingda Liu and also Xiaolei Xie from Tsinghua University. So the topic here is that the empowering the attended home healthcare service. It's we call the AHH. So a robust strategy to pre-schedule on-demand newcomers. So the on-demand newcomers means that for this AHH service, there are some long-term patients and also there are some short-term patients. But for the short-term patient, they arrive randomly. Yeah. So here the on-demand newcomers we refer to the short-term patients. Okay. So in this. So for this talk, okay. So for this talk, here's the outline. So first, I briefly have an introduction. Then I discuss the model, and also actually the model is a variant of a VRP model. So then we use the branch and price cut algorithm to solve the problem. So finally, based on the real data, we conduct a case study to show the performance of our proposed model and also the efficiency of the proposed solution algorithm. Okay. So finally, I briefly conclude my talk. Okay. First for the introduction, the background. So actually, this attended home health care. We use the AHH. Yeah, so, it's a new pattern of the healthcare, especially in China. So it can provide the professional, timely, and also the effective healthcare services. For example, for some regular caring. For example, for influencing, and also for some injection. For some regular injection. So, and also, for this AHH service, it closely aligned with some demand with the lower cost. For example, in UK, this is based on the National Healthcare Society, 2022. The cost is just 20 pound. So for this AHH service, it can also effectively reduce the probability of this readmissions. For example, based on the recent research, it said that okay, so it can the readmission rate can be decreased by 1.39% per visit, and also this AHH service can also has the global strategic constraints. For example, in China, there are 280 million elderly population. So we also care there's a 33 care pattern. And also even for the US, based on the magazine, the report, the budget of the AIDS for the US in 2025 is also $265 million. And okay, so for this AIDS service, actually, here is a typical procedure or the steps. So first for the planning that okay, we hire the caregiver, and we do some related resource allocation, and we distracting the the regions and also the resources. Then after the planning, then we do some operational decisions. So we will do some scheduling. Okay, as we mentioned, for this AIDS service, there are some long-term patients and also there are some short-term patients. So for the long-term patient, there's a regular appointment schedule. There's a, and we do the assignment for the long-term patient, and we do the routine to visit each for giving caregiver, right? It will visit each long-term patient. It's a typical weekly routine problem. And but this is the scheduling. But when we implemented such policies, but there are some on-demand walk-ins. This is we call the on-demand newcomers. They are the short-term patients. They arrive randomly. We don't know. So we have a real-time response to such newcomers or the short-term patients. So yeah, this is for this project is based on a service company in China. So currently they do some manual scheduling problems. So there are some drawbacks, for example, the efficient scheduling and the resource utilization, and also some service delays commonly occurred, and also some in the workit demand response to the short-term patients. So the data will this will cause some loss rate, right? If especially for the short-term patients, if your service is bad, so they will change to another its service company. So based on this motivation, so we want to study the caregiver scheduling and the routing problem. We call the CSRP. Okay, so but for this each service and this CSRP scheduling problem, there are some challenges. For example, how could we ensure the on-time service and completion? For example, the on-time service and completion that okay for each visit for the long-term patients or the short-term patients, we have a time window, right? We should provide the on-time service. So yeah, especially for some situations, right? For some unique conditions, and we have to provide the timely service. For example, this insulin injection, and also for the wound care, and also the heart failure, and some situations. As we mentioned before, so the AIDS service can also cause some patient complaints and make the customers loss. And also even there are also some uncertainties for the caregivers. But yeah, here are some challenges. But there are also we see that okay, the travel time, right, for each visit, the travel time for and also the service time are highly uncertain. And also for this short-term patients, it takes our 20% proportion. It's 20% is if that means that we cannot just regularly schedule the long-term pacing to do an appointment schedule. But once the newcomer, the short-term pacing arrives, how could we dynamically schedule the newcomers? This is also very important. So our goal is that to propose a modeling framework and also efficient solution algorithm to addressing our caregivers scheduling and routing problem under the uncertainty, the two types of uncertainty, the travel time and service time uncertainty, and also the on-demand newcomers. Okay. So yeah, based on the real world data, our industrial partner is this Peng. This is also its company in Beijing. So based on the data, you can see that there's the average service delay is about 9 minutes on average, but with a maximum of 110 minutes. And also the service start time significantly deviates the expected. It has a long tail distribution. So finally, there's also a cascading effect. Cascading effect that the delay amplify and propagate along with the patient visit sequence, right? So here it said that. So here is the patient position daily visiting sequence, but the later the delay is larger, right? The average delay is larger. So this here is so that the service start time has the long tail, Okay. So here is a summary for the literature. There are some the time horizon equals the single or multiple, and also the default. Actually, this is for this CSRP, based on my understanding, is a VIP, right? VIP TW. We go routing problem with time window actually. So and also there are some the solution algorithm. There are some executions algorithm, and also some research they apply the heuristics, and also regarding the uncertainty and modeling paradigm. Sometimes some research they use the reverse optimization, and also trans-constraint and the statistical optimization. So based on the literature we explore, this is the first work to incorporate this on-demand newcomers in the this CSRP literature. Okay, so this is the introduction. So now for the problem. So before presenting the model, I first give you two the menu scheduling policy. And the first policy is we call the designated caregivers. What's the short-term care? So we have so for the caregivers we have the short-term caregivers, and we have the long-term caregivers. Before we mentioned that okay, for the long-term patients we have a regular appointment schedule, right? But once the short-term patient, the newcomer arrives, so we assign some designated caregivers. We call the short-term caregivers to provide the service for the newcomers, for the short-term patients. And the other manual policy is we call the play by ear, which means that okay, so once there's a newcomer, there's a short-term patient arrives, we assign, for example, the nearest caregivers to provide the service. So that's we call the play by ear Pay by year.
I have a question.
Okay.
How do you know whether the patient in the short term? How do you define the short term?
Oh, okay. For the long term is we can schedule for example for next week, so we can schedule before. It is a regular. For the long term is that for example every Tuesday, it is the service or something. Yeah.
So if you have full information, then it's long term.
For information.
If you have full information about what is the demand, then it's long term.
Yes. So to me, in my opinion, I think this short term and long term is just two types of. Long term is that okay before you have some history record for our service.
Okay.
Yeah.
Okay.
Yeah. We just to do some weekly or monthly scheduling.
Okay.
But for the short term patient is it just you for example you from another company you as I mentioned you think that their service is bad. I move to another company.
Okay.
Yeah. So
Okay.
patient type.
Yeah.
No, it's given before. Yeah. It's predetermined. Yeah.
It's a static problem, right?
Uh-huh.
Or is it a dynamic problem?
There's information coming from it. So
Yeah.
Can reverse engineer.
It's not actually it's not dynamic problem. As we will see the formulation. Okay. Yeah. So this is the two manual scheduling policy. We will compare our proposed policy with these two benchmarks. Okay. Yeah. So yeah, actually here's I use this as blue as the long term with the patient type 1. This plus this minus is another patient type. This orange is like the short term patient. Okay. So as you can see, we have two caregivers, right? Yeah, two caregivers, and the short for the first caregiver is that okay, here is a long term patient, right? We schedule, but once there's a type 1 short term patient come here assigned to the caregiver 1. So here is another long term patient with type 2. So for the caregiver 2 is that okay, there are two short term patients. And yeah, so this is one scheduling, right? But for this, we first we put the for our problem we will to cluster the short term patient with a different type. For example, here, yeah, this is our policy. Okay, we schedule the two short term patient with type 1 for caregiver 2, but we put the another short term patient with type 2 for the caregiver 1. Yeah, so here there's some overtime, but for our policy, there's no overtime. It seems to be good. So this is just illustrate the example.
Is there an advantage to have the same type of patient with the same caregiver, like you do minus, like the caregiver has specialties that are better for some? What three different types?
So the different types is you mean for the short term patient, right?
Well, now on the right, it's like you separated the negatives from the positives.
Yeah.
Is there an advantage to that, or it's just?
No. That's the. So in total we have 3. We just we order reschedule the short term patient. In total there are 3, right?
Mm-hmm.
One type 2. One type 1 two type one type two. Okay. Yeah, this is some menu policy. Okay. This is our policy. We want to to cluster the same type of patient. Okay. So we want to minimize the total operating cost, consider the travel time uncertainty and the newcomers in order to provide the on-time service and completion. Okay. So yeah, here's that example. It's the similar example. So here, for example, here there's a newcomer F. As we can see, this blue policy. Yeah, so here we have a different this red yellow. Okay. Yeah, this is the similar example to illustrate our problem. Okay. So here as I mentioned before, the problem here is typically vehicle routing problem with the time window. So yeah, here are some basic the notations and the constraints for the typical vehicle routing problem, right? Yeah. So we have a set of depots and a set of customers with the time window. This is the EI and AR. AR is the latest the service time, and the EI is the earliest. So we also have a set of arcs, and also with for each arc, IG with the travel time TIG. So there are some constraints, right? Constraint meets the customer demand, and this customer is visited once, and also with the specify the time window and the capacity limitation. We minimize the total cost. So for the vehicle routing times with time window, we use the brand and the price algorithm. So right, so we have the FP model, and then we do some relaxation. We have the restricted MP. Then we solve this set partition problem, right? So yeah, this is so we check the reduced cost and to do the column derivation. So we will discuss the algorithm later. So here is a general, it's some basic knowledge for the column derivation. So here, yeah, the algorithm we propose is the branch price and cut. Is the column derivation plus the branch bound, right? Branch and bound. Okay, so here is also a typical procedure to implement the branch and price cut algorithm. Okay, so now we see that we see how could we handle the newcomers in our model? We call that if there are two types of decisions, so we call the static decision. We see that scheduling the decisions for the newcomers are not adaptive to the system state. Just which means that if there are n short-term patients, so we just add n nodes, n vertices in the graph. But instead of the static decision, we consider the adaptive decision, which that scheduling decisions for newcomers are adaptive to the system state. So here is this figure shows that based on the historical data, so we have the patient information, right? So for example, here is some short-term patient. They arrive. So then, based on the information, we can cluster the patient into different the newcomers into different types. For example, there are class and then for each patient we call the division. Then for each type of each patient type, then we do some scheduling. to some adaptive decision. So that's why before, this term nodes is GS. GS is the number, is the set for the short-term patients. So now we have, if we have S types of the number of the types, the patient type is S. So the problem still is increasing. So this is our adaptive decision. Any questions? Okay. Oh, so basically, so how many types of short-term patients based on the information? For the short-term patient, for the newcomer, you have the information, right? You have his location, and also, for example, the location, and also some information like the feature. So, for example, you can use some machine learning, some decision tree, or use some clustering method to get.
You subdivide certain patients into types.
Yeah.
How is that?
Yeah.
How
How many types? In our numerical study, we consider 6. Yeah. For example, the newcomer comes from morning and afternoon. This is so-called some information. Based on the information, then you use some, for example, machine learning methods to do the clustering. Yeah. Okay. Okay. So this is our this adaptive arc flow model for this CSRP. So we mean mandatory cost. This is the hiring cost for the caregivers. This is the transportation cost. And we have a couple of the constraints typically for the VRP problem. But for example, here is some flow conservation constraints, and also but here in our problem, here we have this surface level constraints. So actually it's there's some surface level is no more than a beta. Beta is a threshold, accessible threshold. So in the following, we mainly handle this constraint. This rule actually we use a worst case service level index. It's a type of a risk measure to handle this service level constraints. Okay, so yeah, this is our we call the AAF model. So yeah, so here we see that how could we obtain this division or the patient types. So actually you can capture features of different short-term patients using some machine learning method to obtain a set of divisions or a set of patient type. So actually, here put some classification and regression trees, some methods. This is paper in the Informed Journal optimization. So we can categorizing the nodes for the short-term patients. So maybe to S clusters or to S divisions.
What are you trying to predict? What are you trying to predict?
The predict is just to do the clustering.
Yeah, but the value, you say the value, the mean square, right? So what are you regressing on?
This figure is just this figure is just borrowed from this paper. Yeah.
When you train the machine learning, you have to predict something, right?
Yeah.
You supervise learning on something.
Yeah, just use some of the information, the time, for example, the location and some
Those are
features.
the covariates.
Yeah.
But you're trying to predict what? The travel
Just
time?
to do a clustering.
Unsupervised.
Supervised, yeah.
The regression tree there is supervised.
Yeah. So yeah. So this two figure just borrowed from this picture. Yeah. just to learn, to do a clustering. So for example, based on some features, finally we cluster 6 types of 6 divisions for the pacing type. Okay, so then we consider this travel time uncertainty as I work a lot of robust optimization, so we consider this uncertain ambiguity set. It's and this is the set. We use the t as the travel time. The uncertain distance between the t plus is the empirical distribution to the true distribution p. It's no more than theta. Theta is the size of the uncertain ball. Therefore, this set, it's there are many wonderful properties, right? For example, finite symbol guarantee, and also it's trackable. It's trackable. Okay, so yeah, so now the next step is that how could we calculate the service delay? So actually, given R is the root, and the realization of the travel time, and also the pacing time stability. So we can write this service start time sk plus 1. Then the delay function can be this. We use the ksik plus 1 equal to the service start time minus the latest service time, the latest service time, the time window. So this is the service delay ksik. So but in this proposition, we see that okay, we can write the based on some conditions, we can write this service start time as a some pieces, and also we can recalculate this cumulative total cost C as this. So this is the we calculated this service delay. Then so because the travel time is uncertain, and also this service delay is also uncertain, and it can be represented as a piecewise affine function. So, but for this is the travel time. So, but for the pacing type, we consider pacing type uncertainty. We use based on the information for the short-term pacing, right? We can cluster the short-term pacing into different divisions, but the probability can be uncertain, might be uncertain. So we consider a budget uncertain set for the pacing type probability. So actually it's the P bar, it's a budget uncertainty. This is from the very famous paper from Demetrius, the price of robustness. So here is the GAM, is the budget. We call the budget. So this GAM controls the degree of the deviation. So here the P bar is actually the nominal value, for the type probability. Okay. So here we have to be handle the service level constraint. So we use the service fulfillment risk index. So here is we give here we call the worst case service level index. So the worst case is that okay for all possible pacing probability. So this index actually is reported from the literature. For the VRP problem, they call the risk index, risk index. So yeah, so actually, this row can be also we can use this F worst case sigma to represent over the water stand and liquidity set. So yeah, based on this definition, then we can further to reformulate this worst case level index by this equation 11. Then the next step is that okay, we have a close look at the this worst case service level index. There are some nice properties actually. For example, the monotonicity. It said that if the if the delay is large, so the risk is also large. And also we have the satisfying, which means that if the delay, if there's no delay, if the delay is negative, so which means that you can the risk is 0. The delay is negative means that the service is completed on time. And also we have some infeasibility and also positive homogeneity, convexity, subadditivity, and also probability envelope. This probability envelope provides the bounds for the risk. Finally, we also have this triangle inequality, which said that okay, if you can travel, travel the G1, G2, G2, G3 is a triangle. If the risk you try the first the first and the second axis is greater than the third. So actually, so here the monotonicity and the triangle equality is helpful for our to derive the closed form expression for this worst case service level index, and also the convexity and also this satisfying it's the satisfying risk properties is helpful for us to design the algorithm. Yeah, this is general for this is some general properties. Okay, so here is the rhythm formulation for this worst case service level index. So we minimize the alpha, right? But here we saw that under some conditions, for example, we assume that the trial time, the trial time, has the stochastic ordering relationship. If and also satisfy the triangle equality, then we can to identify set this tall star R. We can identify this a set for the time probability, and then we can get the service delay has some dominance. Has some dominance relationship. This is helpful for us to derive the closed forms expression. So then, how we have an algorithm to to generate to explore this feasible type patient type probability set, and then we can to reformulate this formulation as as the following problem. Then so once we derive this problem, then we can derive the closed form formulation for this worst case service level index. This alpha star we can explicitly write this alpha star. Alpha star, it's the max over the max. So actually, this can further motivate us to to design a efficient algorithm. We first sort the empirical delay, and then we subsequently calculate this alpha star. So once we have this closed form formulation for the worst case service level index, then it can for we can plug in our branch price cut algorithm. So here is here is also the typical procedure for this branch and price cut. So there are three problems. First is how could we find high quality initial solution, right? And then how could we deal with the service level constraints? And then we have the closed form expression. And then how could we find a high quality cut? So for our example, we explore some value inequalities, and also we have some warm up strategies. For example, we use this VNS, this variable neighborhood search to met heuristic to get the initial solution. And also there are some other self-reasoning strategies borrowed from the literature. So yeah, so then we also derive a worst case, the service level index with the dominance rule. This is also very useful for our algorithm. Okay, so here is the algorithm. Then we move to the case study. Yeah, we as I mentioned before, we use the real world data. So actually, we use the year 2019. So actually there are three the size we consider two sizes. This is here is the 5 caregivers, 8 caregivers. 10 is the 10 long-term patients and the 2 short-term patients. For this size is we have 20 plus 5. So we put in the C++ and using the C++ version 21. So we set the hour as the time limit. So we have 5 policies. The first policy is we call the adaptive. This adaptive worst case policy because this is the model we use the BBC algorithm to solve. So the second is the adaptive model with the average fair AVE, mean that for the time probability, for our worst case service level index, we consider we use a budget answer set. But for this average, we just use the nominal value, the p bar, for the type picking the type probability. The other stuff are the same. And also we have a static policy. Then we have our 2 manual policy. This is our 5 policies. Okay, so we first compare this adaptive versus the static. So we can see that this is our adaptive. These 2 are also the adaptive. This is the static. As we can see here, for example, for the last instance, we call this is the small, this is the large. For the last instance, we can see that okay, we can achieve in terms of the unsustainable cost. The worst case policy, it's achieve a lower cost, and also the avenue probability for the lateness, the max probability for the lateness. So here is the smaller the better, right? The smaller the better. So actually, so here it shows that our adapt policy has a better trade-off between the service level and the total operating cost. But as you can see here, but the solution time is larger, right? But this is reasonable, I think, because our model, our adaptive model is larger than the static model. There's okay. So the second policy comparison is we want to explore the value of the patient probability. So we compare the worst case and also you just use the nominal value. So from the this box plot, we can see that in terms of the average expected lateness probability and also the maximum expected latent probability, we can see that our policy exhibits 47% and 50% reduction in the average and the maximum. And also we achieve a lower operating cost both in simple and unsimple. So here we show the the value or the benefit of this type of uncertainty. Then we move to we compare the two manual policies. So this is our policy. This is the two annual policy. But so here it said that, for example, we take the 815 instance. So here in terms of the unsimple cost, our cost is the cost from our policy is lower than them, and even for the maximum expected lateness, average expected lateness. But for some smaller instance, for example, for this 512, for this play by ear, we cannot beat the manual policy. But we also in the appendix we also explore more instances. But we can for some instances we are not we are less we cannot beat the manual policy. But for some performance metrics we are better. And here is just some we illustrate the comparison with the two manual policies. So so here, as you can see, so here is for this designated caregivers. There's some overtime and also there's some idleness. And also for this is also overload. But for our policies, it seems to that we can complete the service on time and also the schedule. We schedule the same time. This is the type, different type. Okay, so finally, have a quick summary. So we study 8 schedule and routing problem on the uncertainties, the travel time uncertainty, and also consider this on-demand working. So we propose worst case surface level everything measure, and also we propose a adaptive model, and finally we design exact BBC algorithm to solve the real world instance up to 14 nodes to optimality. And then we, based on the real world data, we show the value or the performance for our proposed policies when comparing with the traditional and also a traditional static policy and two manual policies. Okay, so this paper is now online, and if you are interested in the topic, you can read the paper. Okay, thank you.